right? We're not going to spend a long time on this slide, right? This is back to the multiple inheritance example, the same one we saw previously. If we try to represent a multiple inheritance hierarchy using this nested notation, it does become complicated, just like the Venn diagram got complicated. So we have to use some kind of hacks, like a double line shows that a class has another parent, right? Array in this nested hierarchy has two parents actually. Ordered collection, which is the top level, an indexable collection, but in this nested notation, it's a difficulty to represent that. So there's a hack about adding a border and a double line in there. So, and string also has two parents, not just magnitude, but also array. So we're not going to spend a long time on that because it's not that important. We want to avoid multiple inheritance anyways. So here's what contracts look like. So they are collaborations that are documented and depicted in this visual form. So there's a class called drawing here, and it collaborates with another class called drawing element. And the collaboration is represented by this directed edge. So that means in this case that drawing is a client and drawing element is a server. So drawing is calling a method in drawing element. And the contract is represented with this ellipse with a number on it, right? And that's a set of responsibilities, essentially. So the drawing class is using a set of responsibilities from drawing elements, and that's what that contract represents. So that's the visual representation. The slides, I just uploaded them to Moodle. So Moodle was working again, and I uploaded the slides. So these can be simplified, like for example, this could represent an entire subsystem, or this could represent a parent class and all of its children. So contracts and collaboration graphs can simplify the visual representation of the communication patterns in the software and the collaborations. So we're talking now about subsystems. What are subsystems? Subsystems are a group of classes or a group of subsystems that collaborate amongst themselves to support a set of contracts. Contracts are closely related responsibilities. So a closely related set of methods and the data that's necessary to carry out those methods. From looking from outside of the subsystem, the classes work closely together to provide a clearly defined unit of functionality. For example, drawing or printing, right? Or maybe storing data. Looking from inside of subsystems, we have a set of classes that are all collaborating with each other, and there may be a complex set of collaborations, a complex flow of information, right? But we don't really want this complexity to be visible from the outside, right? That's the idea. Now, I've put a note in here that superclass and subsystems are not to be confused, right? I guess it's possible to confuse those. A superclass groups a set of classes with identical responsibilities. Remember the is-kind of hierarchy. A subsystem is not an is-kind of hierarchy. A subsystem is a group of classes with different responsibilities that work together to fulfill a common purpose. This is really the is part of object hierarchy, right? If you think of a subsystem, think of is part of relationships, not the is kind of relationships. And subsystems are not inherently different from classes, just a matter of scale. Subsystem contracts represent the services provided by classes in the subsystem to classes outside the subsystem. So conceptually, really, subsystems are like big classes. That's one way to think of them. Just to clarify, a client class is one that requests a server class to perform a task for them. That is correct, yes. When I think of clients and servers, I don't know about you guys, when I think of clients and servers, I'm always thinking about the web. So you have a browser client, right? You have something like Chrome, and that Chrome web browser is a client, right? And it's all it does is it goes around and requests web pages from different servers. Like the client-server terminology is really, in my mind, from the world of networks. It's being adapted here. But if you're ever kind of wondering about clients and servers, think about networks, think about browsing the web. You have a client browser and it's constantly requesting the services of web servers to get web pages, to return different web pages. So here's a visual representation of a subsystem and its contracts. So remember, contracts are just a set of responsibilities. Subsystems support contracts. Collaboration from a class outside the subsystem to a class inside the subsystem is redefined to be a collaboration with the subsystem. The contract used for collaboration becomes a subsystem contract. The subsystem delegates the contract to the class that supports it. So here, contract 1 is delegated from subsystem to print server class. So this outer rectangle represents a subsystem, and the inner rectangles represent classes. So here's a print server class, here's a class called printer, and remember we're using the nested collaboration graph representation. So a dot matrix is a kind of printer, and a laser printer is a kind of printer here. So this is a contract labeled 1, and it's actually the responsibility of the print server class. But it's being used as the interface to the subsystem, the print subsystem. Right? So contract 1 is delegated from the subsystem to the print server class. Subsystems can help to simplify a design near the end of the design process, right? This is one possibility. It can also be used early in the design process for a complicated application. So that's a top-down approach. So what we've been talking about so far is a bottom-up approach where you're starting with many classes and then you're grouping them together. The top-down would be the exact opposite, where you define subsystems first and then you subdivide those subsystems into different classes. This is also a reference to the design patterns. This is what design patterns tend to do. Design patterns, which we're going to talk about next week, tend to start with subsystems and then divide the subsystems into classes. A subsystem might also start out as a class in the beginning of a design if the class gets too big and has too many responsibilities. It needs to be subdivided so it doesn't turn into legacy code and doesn't have too much intelligence. Remember, we talked about centralized intelligence and distributed intelligence. In the end, we still have to define everything in terms of classes, but subsystems can be a major factor in providing an overall global structure to an application. Subsystems are conceptual. Basically, they're conceptual, right? You don't actually instantiate a subsystem when you're building your application. So only their classes exist during execution, but subsystems generally do not exist. However, you can define an interface class, especially for a subsystem. So all classes on the outside of the subsystem that want to communicate with classes on the inside of the subsystem do so going through a special interface class. So in that sense, you could define a subsystem interface, which is conceptually a subsystem. And they do not directly fulfill the responsibilities their classes do. And like we mentioned before, interface classes are often abstract, right? So they define the pattern of communication, but they don't implement it. And that's what this line is talking about. So in order to actually fulfill the responsibility, you need to inherit from the interface class and then add the implementation. So the subsystem concept can lead to more general and flexible contracts and client access functionality via contracts. The new contracts can be added without affecting old ones. And this is a major advantage of subsystem definitions. That means we can make changes to what's happening inside the subsystem without affecting the communication with the subsystem and the objects on the outside of the subsystem. An example of that might be a print subsystem that prints only PDF files, right? But it can be extended to print other types of files, right? Instead of just PDF files. This extension needs a new contract, but the old contracts can still be supported without recoding the old clients, right? So you can support the old contracts, but add new contracts to the subsystem without affecting the old ones. And this is a subsystem card. Remember, we had these class cards, and the class cards have the name of the class, the names of the superclasses, the name of the child classes, a list of responsibilities, and then the list of collaborations. This is very, very similar. So we have a subsystem called a drawing subsystem. And inside of that subsystem, it's composed of drawing class, control point class, and drawing element class. And the purpose of the subsystem is to modify and maintain the drawing. And its main responsibilities are to display a drawing, maintain draw elements, modify a drawing element. So render, edit, and modify. Or render, save, and edit. And these are some of the classes that are responsible for fulfilling these obligations. And this is documented in the form of contracts. So each contract has a number, and then the delegation of those contracts goes to specific classes, like the drawing class, and the control point class. And then when we've defined subsystems, we have to go back and look at our class cards again And instead of the class cards collaborating with other classes, they may end up collaborating with subsystems rather than a class in a subsystem. So this helps abstraction and flexibility. Clients on the outside of the subsystem are insulated from future changes on how the subsystem carries out its contracts or its responsibilities. That's another way of saying we can make changes to the subsystem without breaking everything outside the subsystem. So some guidelines for identifying subsystems. And if this is another forward reference, the design patterns. The design patterns are, you could say design patterns are commonly used subsystems. Anyways, we're going to see more of this topic. Collaboration graphs help to identify subsystems. Look for strongly coupled classes, so classes that are always communicating with each other, right? Or have a lot of shared responsibilities. Coupling is a measure of how much they depend on each other. And coupling can be indicated by frequently used collaborations. By the way, frequency of collaboration does not show up in a static collaboration graph, right? Frequency is a time-dependent behavior, and drawings are static, and they generally don't represent the time-dependent aspects of communication, so they're very limited. Coupling can also be indicated by a web of many collaborations amongst a set of classes that are connected to the rest of the graph with fewer collaborations. Given a set of classes that appear to be strongly coupled, do they work together for some common goal or functionality, like, for example, printing or drawing or editing, or a GUI, for example? A GUI is a very common example. So is data management. Data management is very common. That could include a database, but that can also include a network interface. Do they have a common purpose? Can you name the sets? We'll be looking at examples of these in the forthcoming lectures. Here's a drawing subsystem card. So a drawing subsystem card for the drawing editor to maintain and display a drawing. Its classes can include drawing, control point, drawing element, and its children, by the way. So not all of the classes are listed there. It can be responsible for displaying itself, maintaining the elements in the drawing, modifying an attribute of a drawing element, testing the location of a drawing element, and modifying the geometry of a drawing element. These are the subsystem contracts, and these are the classes inside the subsystem that actually implement the contracts. Contracts are generally abstract, like interfaces, and then if we want to actually implement them, we have to delegate them to a class, right? Because subsystems are conceptually, generally speaking, they're not instantiated. Okay, here's a visual representation of a subsystem, right? That same subsystem, it's the drawing subsystem again, right? It's this one. Inside we have a drawing class, a control point class, and look, there's another, okay, this is a class hierarchy. So drawing element, group element is a kind of drawing element, text element is a kind of drawing element, and linear element is a kind of drawing element. These are three contracts with the subsystem. So contracts 1, 2, and 3, right up here. And then these contracts 1 and 2 are delegated to the drawing class, And number 3 is delegated to the control point class, right? That's indicated in the... And 1, look, 1 appears again in the drawing element parent, and 4 appears in the drawing element parent, and so does 5. So those are the actual classes that implement the abstract contracts. Here, now this is using the notation of the object-oriented programming book. This is that same subsystem represented in UML. So this is the drawing subsystem. It has the responsibility, for example, to display. And notice how it's using text. Instead of a number, it's using text, which is actually better, I would say. And here it's, instead of a number representing a contract, it's using the words maintain elements and define new geometry, right? And it's delegating those to the drawing class and the control point class. And look, I think this is confusing, but there it is. What can you do? We have collaborations and class hierarchies mixed together in the same graph. It is confusing, but hello, that's not my decision. Here's the class hierarchy. So the group element is a kind of drawing element, the linear element is a kind of drawing element, and the text element is a kind of drawing element. And then these contracts are defined inside the subsystem and delegated to the parent called drawing element, right? So it's yeah, it's confusing, and that's the way it is. So we have collaboration or patterns of communication together with the is kind of modeling. I prefer not to mix these two together, but here they are mixed, and you will see them mixed in other UML diagrams as well. Here's another example. Oh, here's a question. So the to display means the same contract. Yes, that's correct. The to display is the same contract, but it may have different implementations. The implementation depends on the class that implements it. So yes, that is correct. It's the same contract. Yes, the collaboration is the same, the contract is the same. So you can imagine a drawing subsystem, and it has a display method, a method called display, right? What does that drawing subsystem do? It could, one possibility is to take that message, that display message, and then pass it to every element inside the drawing subsystem. So drawing then has a method called display. So a drawing knows how to display itself, right? The same could be true for control point, by the way. And then the drawing could pass on that responsibility to a drawing element. So the drawing just passes the message along to every drawing element inside the drawing. And then every drawing element knows how to draw itself. So a group element knows how to draw itself, a linear element knows how to draw itself, text knows how to draw itself. So you can imagine that kind of implementation for these concepts, right? A drawing subsystem knows how to draw itself or display itself. It passes that message on to the drawing object, then the drawing object passes the display message to every individual polygon and element inside the drawing. Here's another example, an editing subsystem to handle the user interaction for editing a drawing. So it has classes drawing, editor, and tool and its children. It has two contracts, interpret user inputs, and activate, handle mouse input, and deactivate. So there's 6 interpret user inputs. It's a very, very loose language. And then 7, which is to activate, handle mouse input, and deactivate, right? So we have the editing subsystem, which consists of the drawing editor. And then we have tool, which is that hierarchy. Creation tool is a kind of tool, selection tool is a kind of tool. And this is what the editing subsystem looks like in terms of collaborations and contracts. Here's the same representation, the same subsystem, but represented in UML. So interpret user input instead of a number, which is helpful. And then mouse handler, which is also helpful. Right? And then we have this mixture again of is part of relationships and is type of relationships mixed together again. Here's another example of subsystems collaborating with other subsystems. So this is a very high level design diagram of a piece of software. Here we have the GUI, and then we have an editing subsystem, and then we have a drawing subsystem, right? If we look at this carefully, these kinds of subsystems, there are certain subsystems that come up over and over and over again for basically 90% of all software. GUI subsystem, like a GUI, that can be a subsystem in any application with a graphical user interface, right? This unit here is a processing subsystem. Most applications are going to have a processing subsystem. They're going to take user input, do something with it, like process it, and then return the results. And the other subsystem the subsystem that's missing here that's very common is the data subsystem. Usually there's an interface to a large set of data. It's either going to be stored in a database or a file. Like in this drawing editor example, what's missing is the file I/O subsystem, because these drawings are going to be saved in files. That could theoretically be encapsulated in the drawing subsystem. But I guess what I'm rambling about is you're going to see the same subsystems over and over again. A contract is just a set of responsibilities. That's all it is. Here's the same set of subsystems represented in UML. So we have a GUI application, we have editing subsystem, and then the drawing subsystem, right? And we don't use numbers anymore. We replace the numbers with text. Okay, so I'm trying to finish a little bit early. If anybody is upset about that, let me know. But I was hoping to finish maybe 10 minutes early. So simplifying interactions, subsystems should help to simplify class interactions. That is the whole purpose, is to simplify the visual representation of a piece of software, but also not only the visual representation, the actual implementation. The more complicated the interactions are in a piece of software, the more difficult it is to maintain and debug, right? I think a lot of you have heard this phrase, spaghetti code. Spaghetti code describes software with just these almost a random set of collaborations where every class is communicating with every other class, and the pattern of flow of information and execution is very, very chaotic, essentially. We're trying to avoid that. We're trying to basically simplify the patterns of communication inside the software. That's really what we're doing with subsystems. So simplifying interactions, simplifying the collaboration graph, simplifying the patterns of communication, right? So if we see areas of complexity in a graph, this is a good area to think about subsystems and introducing subsystems that simplify the design, right? Any proposed changes should simplify the collaboration graph. So here are some guidelines for simplifying collaboration patterns. Minimize the number of collaborations of a class with other classes and subsystems. Minimize the number of classes to which a subsystem delegates, right? That's possible with interface classes. And minimize the number of different contracts supported by a class or a subsystem, right? That makes it easier to change the classes and subsystems for future references. So a little bit more detail, minimize collaborations of a class. A design is simpler with fewer collaborations, right? The collaborations are represented by those edges in the graphs, right? If you have a graph with thousands of edges in every direction, it's going to be hard to maintain. Reduce collaborations, especially outside the class's subsystem, right? That's a great design principle. Can we reassign responsibilities or redefine contracts to create fewer collaborations? So the idea is to conglomerate communication to a subsystem into an interface. That's the idea, right? Create a subsystem interface class to help hide the implementation details of the subsystem from outside the subsystem. So here's an example, right? Here's an example of the print subsystem again. The print server class is a print subsystem interface. So that the print server class, right? So we want to hide the details of specific printers from a user. So we can redesign to add forms of facilities that are not clean. It bypasses the print server. So in other words, we can define, if we want to encapsulate behavior, we define communication with contracts to the subsystem as opposed to classes inside the subsystem. Right? The first contract is print a file, or the first responsibility is to print a file. The second one is to send the file to the printer. And then the third one is to associate form with the printer and notify the user when the printer is finished. So minimize delegations. By minimizing the number of classes that receive a subsystem contract delegation directly, you hide more of the subsystem, get better encapsulation of the subsystem. This is, again, is encouraging the idea to introduce interface classes that encapsulate all the communication that flows in and out of the subsystems, right? A well-designed subsystem limits the number of classes that are delegated contracts, right, and a larger number of internal collaborations. So we're trying to centralize or bring together all the communication that happens inside of a subsystem. Here's an example of this in action. We have a so-called inventory control. So imagine a store. It has a cash register. If you get confused, cash register is called a till in the UK. And we have a cash register bringing in all the money. We have a cash register operator. We have all the goods that are being sold in a warehouse. And we need to have a system that keeps track of the inventory. In other words, what have we sold and what is still remaining in the warehouse. So look, the cash register right now is collaborating with the inventory item, the transaction log class, and the accounting subsystem. And the same is true for the warehouse class. It's collaborating with all of these classes through this subsystem, and it's a complicated set of collaborations. It's a complicated set of communication, right? If we make changes to the accounting subsystem, it might break the pattern of communication with the cash register and the warehouse. So what we do is we introduce a new class called Inventory Manager, which is an interface class, right? Then the cash register collaborates only with one class, and it's the Inventory Manager, right? This subsystem, the inventory subsystem, is essentially introduced by this one inventory manager class. And all the communication goes into the inventory manager class. And the same is true with the warehouse. So warehouse communicates with the inventory manager class, and then the inventory manager class shields the complexity of the inventory subsystem from any object that's outside the inventory subsystem. I hope that makes sense, right? It makes sense when you look at the graph, how simplified the graph is. Minimize contracts of a subsystem. So too many contracts in a subsystem may be a sign of too much intelligence. Try to break such a subsystem into internal subsystems. So this is a subsystem, this rectangle. And you can communicate with this subsystem through 1, 2, 3, 4, 5, 6 different contracts. So that's complicated. We could define a subsystem with this represented by this bounded edge. And this subsystem only has 2 contracts. So you can only communicate inside the subsystem through these 2 channels, through these 2 contracts. And then these contracts are delegated to 2 classes inside the subsystem. So the pattern of communication between the inside and the outside of the subsystem is much simpler in the example on the right. I hope that makes sense. So we've simplified. In this case, we can reduce from 6 contracts to 2. That was the idea, by introducing a subsystem and then consolidating the communication in an interface class. Okay, that's basically it for subsystems. And then after we've defined our subsystems, we have to go back and revise our class cards. Remember, we wrote down class cards for all the classes we identified. So that means we need to revisit all of our class cards. We have to look at the contracts to make sure they're up to date with the new subsystems. We have to look at the collaborations and make sure they're up to date with the new subsystems we've introduced. We've probably introduced new classes, new interface classes that handle the communication to subsystems. And we might need to do quite a bit of revision to our original set of class cards in order to bring it up to date with the new subsystems. All the drawings might have to be revised, like hierarchy graphs might need revision because of new subsystems. Collaboration graphs are certainly going to need revision because of the new subsystems. And we may need to perform some more walkthroughs. Right, and these are all consequences of introducing these new subsystems and new interface classes into our design. Okay, any questions? Yes. I missed the response before. Is a contract just two classes working together? Yes, that's correct. A contract is just two classes communicating, or a set of responsibilities. It's just a set of responsibilities, essentially, right? This is a contract represented in visual form. Any other questions? I see it's dark now, which is not very exciting. Okay, I hope that everybody has a great weekend. Next week's lab is again going to be fun. Next week's lab, we're going to start working on the coursework. So the next week's lab actually integrates work with the coursework. So let's bring your questions about the coursework to the next lab. The next lab, by the way, is about a very exciting topic, and that is debugging strategies. A set of systemized rules or guidelines to help you debug code, right? It's a huge topic, debugging, and you spend a lot of time debugging. It would be very interesting to know how much time is spent on debugging actually, but it's a huge part of developing maintainable software and just software development in general. So having a good set of debugging strategies is very, very valuable. And that's what we're going to talk about in next week's lab. And we're going to apply those debugging strategies to the coursework, basically. So it's going to be really beautiful. Anyways, I hope everybody has a great weekend, and yeah, we'll talk again soon.